All right, so officially picking up where we left off. We had covered sections 4, B, and C, but we had not discussed these special cases in terms of the substitution and elimination method. We had actually seen pictures of them back in 4A, and I mentioned we'd see them again. The idea is you don't realize you're dealing with a special case when you start a problem, so you would just start these like any other problem. For these first two on this page, we will use substitution as if that was our method. So with substitution, I'm going to go ahead and take this first equation. And remember, substitution involves the first step of solving one equation for one variable. So we will solve it for y. I will get the y by itself. And so that puts me 5 minus 2x on the other side. Now that we have y equals 5 minus 2x, y is the same as this 5 minus 2x. And so with substitution, we will take it and substitute it into the other equation. We always go into the other equation, replacing the y there with that collection of terms there. So this equation will now look like 2x equals 3 minus, but now here is a case where certainly substitution, it is important for us to use parentheses. So replacing the y with this 5 minus 2x. And the reason that's important, very important here, is we're subtracting y, so we have to subtract the entire set of terms. We need to distribute that minus sign, almost like it was a -1 through both those terms to clear those parentheses, giving us a minus 5 and a plus 2x. So at that point, we continue solving the equation. We have a couple of like terms we can combine there on the right. 3 minus 5 is -2. Now at this point, we would need to put our x's, our variable terms, on the same side. And no matter which one you look at, moving or doing the opposite of, we're going to be removing this 2x here with a minus 2x, but it also cancels there. So what we see on the left side, there's nothing left. You don't want to write 0x. There's no real reason to do that. It's 0. There's nothing left on that left-hand side. On the right side, just a -2. So what we have here is the step where we focus on our variables. After that step, we have no variables, right? This step right here is the key thing you want to look for, right? The key occurrence is that our variables disappear, right? That we have no more x's in this equation whatsoever. So when that happens, when the variable disappears, that's when you know you're in a special case. And we saw that back in chapter 2, the same exact idea. Solving for an equation, variable disappears, special case. Now the question of which special case is it relies on what you're actually left with. We're left with a statement of 0 equals -2. Well, that's obviously not true. 0 does not equal -2. And so just like in chapter 2 with regular equations, we mentioned that if you're left with a statement that you could say is not true, not correct. Basically, if this does not make sense, then the thing we're trying to solve doesn't have an answer that will make it make sense, that will solve it, right? This is telling us that our original problem doesn't have an answer. And so, in this class, the way we say that is the two-word phrase, no solution. So that same phrase that we used in chapter 2 to describe a problem that doesn't have an answer, right? Solution is our word for answer in equations, the solution to the equation. So that system of equations doesn't have an answer, and we know it as soon as that happens, as soon as those variables disappear. So there's one example with substitution. Let's go ahead and take a look at another example, though, because we do have two special cases to worry about. No solution was one of them. So with this system, notice I already have an equation that says y equals. So that's useful because I can take this collection of terms there that y is equal to and immediately substitute it in for the other equation for y. So taking this equation, having x plus, now in this case, for plugging in for y, you actually don't need parentheses since it was just preceded by a plus sign. You can put them in, but they don't really make any difference to the problem. So I can actually just replace that y with that 3 minus x and have that equation there. From there, again, let's combine some like terms. For the first step, we notice we've got an x minus x on the same side. So that's 1x minus 1x. Well, those combine and give us nothing, 0x, gone. So if those are gone, I'm left with a 3 on the left and a 3 on the right. But again, the important thing is right there, let's start again, here's where you know you're in one of the special cases. You then look at the next line once the variables are gone to figure out which special case you're in. Now here it says 3 equals 3. And unlike the other one that was not true or never true, to say that 3 equals 3, well, yeah, that's always true, right? That's always a true statement. Now, the phrase all real numbers was the phrase that we saw as a special case answer back in chapter 2. That doesn't really make sense here, and you have to go back to the stuff we talked about in 4a to get a better picture of it. But the idea was we saw this happen when these two lines, these two equations, were equations of the same line. And in fact, you could reorder them to make them look identical and realize they are the exact same equation of the same line. So what that means when we see this is we've got two lines, and the whole idea graphically when we're trying to solve this was we're trying to find the point where these two lines intersect. Well, these two lines are the same line. So asking where they intersect is like asking what points they have in common, which would be every single point on that line if we were to graph it. And so the way we say what the solutions are to this system, there's a lot of them, essentially any point on the line. And so our three-word phrase for that is, not all, is infinitely many solutions. That's our way of saying there's a whole lot of answers, an infinite number of them, an infinite number of solutions, because it's every single point that's on the graph of that line there. It's not all the points, because there's plenty of places that those two lines don't intersect, but that's where we saw that phrase again back in 4a as well, of infinitely many solutions. Also, just as a quick reminder, we did see this also back in 4a, and we saw the no solution special case when the two lines you were working with were actually parallel lines and never crossed. So that's where that answer comes into play as well. So there are two examples of our special cases using the substitution method.